Good morning. In today's lecture, we'll talk about how to describe the quantum state of a system of 2 qubits. And in the process, we'll talk about a very fundamental concept, that of entanglement, quantum entanglement. Quantum entanglement is probably the most important concept in quantum information, quantum computation. It's the key resource that makes exponential speedups possible in quantum computation. In fact, one way one can describe it is quantum computation, quantum information are an exploration of quantum entanglement, something that was discovered in the early days of quantum mechanics and then not really pursued to much depth. So entanglement was discovered by Einstein, Podolsky, and Rosen. And Einstein later described it once derisively as spooky action at a distance. So entanglement is a very counterintuitive concept, and in today's lecture and the next lecture we'll try to come to grips with this concept. Now, actually there's a quote from Erwin Schrödinger which I found very interesting because this is from the 1930s, where he already talked about, he says, I would not call entanglement one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So this is a remarkably modern viewpoint on entanglement. Okay, but before we do all this, I'd like to do a review of what we've seen so far. So what we've studied so far is what's a qubit. And our model of a qubit is, well, we've been describing it in terms of atomic qubits, in terms of the energy levels of an electron. And we are thinking of 2 distinct energy levels, the ground state and the first excited state, which, if this was a classical system, we could use to store a bit of information, encoding 0 as the ground state and 1 by the excited state. But of course, in quantum mechanics, the electron doesn't make up its mind whether it's in the ground or excited state in general. And it can be in a superposition of the ground and excited state, where it has some complex amplitude of being in the ground state and some other complex amplitude of being in the excited state. The interesting thing being that these amplitudes are complex numbers, and they are normalized. Okay, so in general, you're in the state alpha 0, 0 plus alpha 1, 1, where alpha 0 and alpha 1 are complex numbers, and the sum of the squares of their magnitude add up to 1. So it's normalized. Okay. The normalization condition is interesting because when we actually go to look and see which state the electron is in, it quickly makes up its mind and it ends up in the ground state with amplitude alpha 0 magnitude squared, and in the excited state with amplitude alpha 1 magnitude squared. Moreover, as soon as we make look, the state of the system is disturbed and the new state is exactly consistent with what we measured. So if we were to look at this example that we had earlier, the probability that we'd see 0 would be 1 over square root 2 squared, which would be 1/2, and then the new state would be exactly the 0 state. And the probability that we'd see 1 would also be 1/2, because that would be 1 over 2 squared plus 1 over 2 squared. And the new state would now be the 1 state. Okay, so all this we saw last time. We also saw that there's a geometric interpretation of what it means to have the state of the qubit. So for example, let me just use real numbers. So let's say that the state of the qubit was 1 over square root 2, 0 minus square root 3 over 2, 1. Sorry, that doesn't add up, so I should actually, let's say it's 1 over 2, 0 plus square root 3 minus square root 3 over 2, 1. So you can see it's normalized. Now, the geometric interpretation says that the state of this qubit is a unit vector in a two-dimensional vector space where the axes, the coordinate axes, are labeled with 0 and 1, the ground and excited state, and the state of the system sits on a unit circle, and we can plot it out here, and it might look something like this. So this would be psi. Okay. And now there's also an interpretation of this in terms when we do a measurement. What we are saying is that the state collapses to the 0 state with probability cosine squared theta, and it collapses to the 1 state with probability, well, cosine squared of the angle it makes with the 1 state, which actually ends up being sine squared theta. So this is the probability of 0, and sine squared theta is the probability of 1. Okay, now, okay, let me just give you a couple of other examples of qubits. So it turns out that photons, particles of light, have a qubit associated with them, which is called the polarization, which is roughly the orientation of the electric field oscillations associated with this, and we can think of these oscillations as either being horizontal or vertical, and that corresponds to a qubit. The spin of a particle, like an electron, is a quantized version of its angular momentum, and it also forms a qubit where the spin is either pointing up or down. So now, how would you measure these qubits? Well, in the case of photon polarization, this is particularly easy. It's it's in terms, you do this with a polarizing filter, where the filter, depending upon its orientation, it might allow photons that are polarized vertically but not horizontally. So think of the photon sort of moving horizontally. The polarizing filter is orthogonal to it, and it's aligned, let's say, vertically. So then it only allows photons through that are polarized vertically and blocks photons that are aligned horizontally. But of course, in general, the state of the photon, so let's say this is horizontally polarized, that's vertically polarized. So in general, the state of a photon will be some superposition of vertical and horizontal. It's going to be alpha times horizontal plus alpha 0 times horizontal plus alpha 1 times vertical. And so if you were to pass such a photon through this filter, then the net effect is it gets blocked with probability alpha 0 squared, and it's transmitted with probability alpha 1 squared. If it's transmitted, then its new state is vertically polarized. Okay, so this is what you see when you hold up a polarizing filter. You see photons coming through, and they're polarized in various different directions. But of course, well, the ones that are horizontally polarized are blocked, ones that are vertically are transmitted. The ones that are polarized diagonally, they're transmitted with some probability, but then what you see is vertically polarized photons only. Okay, well, there's another question you could ask, which is, what happens if you orient this filter so that it's not aligned either vertically or horizontally, but rather diagonally at a 45-degree angle? Well, it makes sense that what it would do is allow through those photons which are at a 45-degree orientation, but block everything which is at a minus 45 degree orientation. So in terms of the qubit picture, here's what it corresponds to. What it corresponds to is that we are now measuring in this diagonal basis, where this is plus and this is minus. So now if we started with a photon in this particular state, the probability that it will go through is given by cosine squared theta, where theta is this angle. And the probability that it's blocked is sine squared theta. Moreover, if it goes through, then it must be oriented in a diagonal at a 45 degree angle. Okay. So this is how measurement at in an arbitrary orthogonal basis works. So this is what it means to measure at an arbitrary angle. Now what happens if you take two of these polarizers and you align one horizontally and one vertically? Well, if you look through it, well, you have lots of light coming through. Some of it passes through the horizontally polarized one, some of it passes through the vertically polarized one. But where the two intersect, you see a dark patch. And the reason is simple. The light that's coming through, it might be, let's say we had only one photon coming through. Well, it might be polarized diagonally, alpha 0 horizontal plus alpha 1 vertical. And let's say this first polarizer it goes through is horizontally aligned. So then with probability alpha naught squared, it goes through, and now the light is horizontally polarized. But now it's blocked with probability 1 by this second filter. And so the net effect is, no matter what its original orientation, it's definitely blocked by the two filters in conjunction. But now you can do a very interesting experiment. What you could do is, between these two filters, you could insert a third one, which is aligned at a 45 degree angle, or pi by 4. So this is our third filter, which is inserted between the two. And now what happens? Well, the interesting thing that happens is that this middle patch is no longer dark. And the reason is, some of the light that comes in, it goes through the first filter, but now it's horizontally polarized. None of it would get through this second filter, but on the other hand, we have interspersed this third filter in the middle, and that's at 45 degree angle. And so these horizontally polarized photons get through this middle filter with probability half. Okay, so through the middle filter, they get through with probability half, and then the output, the photons that get through, are polarized at a 45 degree angle. Now when they try to get through the second filter, which was vertically polarized, they again get through with probability half, because they are oriented at 45 degrees to the orientation of this filter. And of course the photons that get through are now vertically polarized. Okay, so that's it as far as measurement goes. Now if you remember, we also had this notion of the uncertainty principle for qubits, where we could measure the qubit either in the bit basis 0, 1, or in the sign basis. So remember, this is our bit basis 0, 1. This is plus and minus. Plus is where plus is an equal superposition of 0 and 1, and minus is an opposite superposition of 0 and 1. What the uncertainty principle tells us is that we cannot know both the bit value and the sign value simultaneously. In other words, suppose we were to measure in the bit basis, well then we know that our qubit is either in the state 0 or in the state 1. But now it's maximally uncertain with respect to the sign basis. And vice versa, if you were to measure in the sign basis, we are maximally uncertain with respect to the bit basis.